Hello, everybody. I'm going to go through a topic known as stoichiometry. Um, stoichiometry, at its very basic level, is just measuring quantities of stuff or calculations involving quantities of stuff. So, you've done some of that mole to mole, mole to mass. Those are all calculations that are kind of the basic intro to stoichiometry. But the nuts and bolts come with being able to deal with a chemical reaction and calculating quantities in a chemical reaction. So let's start with one. So here's a chemical reaction. In this particular instance, we have CH4, which is methane, reacting with oxygen to produce carbon dioxide and water. Now, the problem we have first is that we don't have a balanced chemical equation. You can't do any stoichiometry without a balanced chemical equation. So let's start by balancing it. Well, I I have four hydrogens over here and I need four over here. So if I put a 2 in front of that, and we can only use what we call coefficients, that is numbers in front, to balance. Now I have 4 on the left and I have 4 on the right. So that's balanced. But as I move along, I notice that I've got 2 oxygens here. And over here, counting everything, I've got 4. I've got 2 right here. And I've got 2 over here because I've got this coefficient in front. So in order to have 2 there, I need to put a 2 in front of that. Now my equation is balanced. I have 1 carbon and 1 carbon, 4 hydrogens, and 4 oxygens on both sides. So now we can do some stoichiometry. Now that, and to be honest, I mean, even just having the balanced equation is stoichiometry. Balancing equation is the first step in any stoichiometry problem. So I have a balanced stoichiometry problem, or a balanced chemical equation. And one way to interpret this, and the very basic way to interpret the quantities in this, is that I have, in this case, I have, let's do this. I have one of these. I've got 2 of these, 1 of these, and 2 of these. Okay? And what does that mean? Well, I could interpret it as 1 molecule of CH4, 2 molecules of oxygen, 1 molecule of CO2, and 2 waters. But the way we typically interpret that is moles, because individual molecules we can't see them, so we count in large chunks called moles. And so I have 1 mole of CH4, 2 oxygen, 2 moles of oxygen, 1 mole of carbon dioxide, and 2 moles of water. Now, let's say, for instance, that I don't want to react for 1 mole of methane. Let's say instead I want to react. I have 4 moles of this. So I've got 4 moles of CH4. Well, that means I'm going to react 4 times the amount of quantities in this equation. So that means that I will need 8 moles of oxygen, 4 moles of carbon dioxide, and 8 moles of water. And that means that, for example, if I wanted to know how much water is produced from 4 moles of methane, I know I would get 8 moles of water. Okay, well, that's all well and good, except that we may not be using whole numbers. So let's suppose we have parts of it. Let's say instead I wanted to react 0.25 moles of methane. Well, I know that in this reaction, the ratio is 1 to 2. So I'm going to need twice as many moles of oxygen, which would mean I'd have to have 0.5 moles of O2. And it is a 1 to 1 ratio of methane to carbon dioxide. So it would produce 0.25 moles of carbon dioxide. And then water, it's a 1 to 2 ratio. So again, I would get 0.5 moles of water. Well, the problem we run into is that this is what we call a mole to mole conversion. Well, the problem is we can't measure in moles. We don't have any instruments that allow us to measure in moles. So let's take a look at how many grams that would produce. So again, let's say I start with 0.25 moles. And by the way, we abbreviate moles MOL because we can't use ML because that's milliliters. So we use MOL to abbreviate moles. And I want to know how many grams of water I might get. Well, since it's a 1 to 2 ratio of methane to water, I know that I'm going to get 0.5 moles of water, but I need to convert that to grams. And the way we do that is we multiply by its molar mass. And the molar mass for oxygen or water is 18 grams per mole. And so I would get 9 grams of water. It's probably best that you solve that with dimensional analysis. Just get in the practice of it. If I have 0.5 moles of H2O and I want to convert that to grams, well, I know that there are 18 grams per mole of it. That allows me to cancel the moles, and I get 9 grams. Okay, well, that's the conversion when we're starting with moles. But let's suppose that I start with mass. I'm going to start with, let's start with 10 grams. 10 grams of CH4. And I want to know how many grams of water is produced in this equation. There's a couple of different ways to do this problem, but I'm going to show you how to use dimensional analysis to solve this. I'm going to start with my given 10 grams of CH4. Okay, so I need some conversions, and one conversion I have is molar mass. When you're doing stoichiometry, you're going to be using molar mass a lot. That is the number of grams in 1 mole of a substance. In CH4, I've got carbon, which is 12, and I've got hydrogen, which is 1, and I've got 4 of them. So that's going to be a total of 4. And I add those up, and that's 16 grams. So 16 grams of CH4, and you may want to write in what it is you're talking about, because you can't cancel grams of one thing with grams of another thing. And that's per mole of CH4. Then I have my equation up here, which is my recipe for reacting CH4 with oxygen. And in my recipe, it's a 1 to 2 ratio here. So 1 mole of CH4 will produce 2 moles of water. So far I'm able to cancel the grams of CH4, the moles of CH4. But if I stop there, it would be in moles of water. I don't want moles of water. I want grams of water. Well, I'm going to use molar mass again. And in this case, I have 2 waters, that's 2, plus oxygen, which is 16. And I'm rounding everything to whole numbers here. That's a total of 18. That is the molar mass of water. So water is in 1 mole of it, and I want to put the moles on the bottom, of water, weighs 18 grams. So I can cancel my moles of water, 18 grams of water. And now it's simply a matter of crunching the numbers. And when I crunch the numbers, I get 22.5 grams of water, which, since I was only given, let's assume both of these were significant, probably should have written it as 1.0 times 10 to the first. So you would know that that is exactly 2 sig figs. So I'm going to round up, and I'm going to say I get 23 grams of water. And that is how we determine the amount of substance that is in a chemical reaction. Now, I could have done this for anything in the reaction. I could have determined how much oxygen in grams I would need, or how much carbon dioxide I'm going to get. I would use the same method and go about it the same way. I can determine the amounts of anything in the reaction that I want to, just by using some dimensional analysis.